because you couldn't pull the quarks out of the proton. You hit the protons hard, the quarks never came out. But if they're moving freely, what's stopping them from coming out? And that eventually led us to discovering a new phenomena, which led us to the theory behind this strange behavior, and turned out to be the theory of the nuclear force. And I'll spend a bit on the physics here because it's interesting. It all depends on the properties of the vacuum. Now, the vacuum, you might think, is pretty boring. And that's true in the classical world. The classical vacuum is empty. You know, if you take everything out of this room, all the people and the air and the rug, the furniture, and you're left with nothing, that's the vacuum, right? Boring. This is a picture of the classical vacuum. Or here's a better picture of the classical vacuum. I like to tell my friends that, you know, what particle physicists do most of their life is study nothing. Study the vacuum. In order to understand particles and their behavior, we have to first understand nothing, the vacuum. Now, the reason the vacuum is much more interesting than this picture is that in quantum mechanics, nothing can be this simple because of the uncertainty principle. Because let's say I really want to study the vacuum, then I probe it. I hit it with a photon, a quanta of light. I shine a flashlight on it, like this. And if I hit it, I disturb it. Now the vacuum is the arena, space-time, the arena in which the fields of electricity and magnetism, the electromagnetic fields and other fields live. And when I observe them, I give them a little kick. They fluctuate. Let me show you a picture, an illustration of what the vacuum really looks like. And I can do this because I'm a theorist, so I can calculate in a good theory what the vacuum really looks like at the nuclear scale, using QCD, of course. This is a picture of the quantum vacuum, which will be full of fluctuating fields. These are fields like the electromagnetic field, but these are the fields that transmit the strong nuclear force. And here it is. This is a calculation done using QCD, or theory of the strong interactions, put on a lattice, discretized, massive computer calculation of fluctuations in the fields that live in the vacuum on the scale of the nucleus. This is about the size of the proton. Here to here. You don't see that because you can't resolve distances that small, 10 to the minus 13 centimeters. But it's there. The vacuum is a very interesting place. You can have interesting dynamics. And it is the property of the vacuum in a theory like quantum chromodynamics that gives rise to the phenomena that we discovered that led to that theory. The phenomena that if you take quarks and you put them very close together, the force between them is very weak. And the closer they are together, the weaker the force is. That's the phenomena of asymptotic freedom. Which also explains why you can't take the quarks out of the proton, because when you pull them apart, the force gets stronger. And the quarks are confined, held together permanently inside the proton. That's confinement. Well, that was a very nice discovery, and it was only true in one kind of theory. So it led us to a theory later called quantum chromodynamics. It's a theory like electricity and magnetism where the quarks have a charge, except there are more charges than just one electric charge. There are 3 charges. And so the theory is richer, more complicated, more interesting. And by now it's understood that this theory really works with great precision and describes the nuclear force and the properties of the proton, the neutron, and all the particles you can create in energetic collisions between protons. We can now calculate the mass of the proton and the neutron and the other nuclear particles. Well, that's what led to this. That's the King of Sweden. When you get a Nobel Prize, you get a check, which he's giving me here. You also get a certificate, which has a beautiful picture illustrated by a Swedish artist. And you see what he drew here was a proton with 3 quarks, which can't get out. In fact, they made a poster for the Nobel Prize that shows these 3 quarks trying to escape from the proton, but frustrated because the force is getting stronger and stronger and holding them back. It's a very pretty cartoon, but they got it wrong. Here they have these springs, these forces acting on a triangle like this. Here's a picture of what actually happens according to the calculations when you try to pull the quarks out of a proton. You see that you form the field lines form this triad, also preventing the quarks from getting out. This again is a massive computer calculation in QCD. Okay, enough with physics. Let's turn to second area where we've made rapid advances, cosmology. There it is amazing how rapid things have changed. In 1 century, 100 years, we've learned that the universe is enormous, and our sun is only one of 100 billion stars in the Milky Way. But the Milky Way is not the universe. There are 100 billion galaxies in the universe at the moment. And we learned that the universe is expanding like a balloon that you blow up, the surface of a balloon, expanding with almost a constant rate of expansion. And we learned that that expansion began about 13.7 billion years ago from some very hot state, which we call whimsically the Big Bang. We've expanded our horizons from the size from the Earth to the solar system, to the galaxy, and to the universe, the visible universe as a whole, which is about 10 billion light years, the distance light travels in a year across. This is a picture of the universe as a whole, which shows very little structure. And we understand roughly, to a good extent, how this universe developed from a very, very small region of space. We understand most of the history of the universe. From some kind of beginning, a very small region of space, we believe, expanded very rapidly, then settled down. We have a picture of the universe at close to the beginning, 200,000 years after the beginning, this is what it looked like. This is a picture of an almost uniform gas of light that when atoms, the universe expanded, it cooled, atoms formed out of electrons and nuclei. The atoms are neutral, the light streams through, and this is what we see 13.5 billion years later, that light hitting our eyes. And that light tells us that back then, the universe consisted of this gas of atoms and light, which was almost completely uniform, and the variations in color here blown up by a factor of 10,000 show the little variations of density in that almost uniform ball of gas. But gravity attracts particles together, and regions that are more dense get pulled together, regions that are less dense don't, structure begins to form, and we now can follow that emergence of structure through the formation of stars to galaxies, planets, and we're about here. And most recently we've learned that this sort of constant expansion of the size of the universe is actually accelerating due to something called dark energy, and might continue to accelerate forever. All of this history we've deduced from almost nothing, no understanding, in 100 years. The biggest mystery remains the beginning, the Big Bang, where still all of our equations break down. And now a good part of cosmology and astrophysics, and certainly the kind of physics I do now, string theory, would love to try to explain the Big Bang itself. That's the biggest unknown that is left. That and the question about what is going to happen in the future. Will the universe expand, indeed, in an accelerated way forever? But most of the history, back to the first billionth of a billionth of a billionth of a billionth of a second, we understand. It's quite remarkable, just 100 years. Finally, a word about the youngest of the sciences, in many ways, biology, which we're celebrating 150 years for this year, last year, of Darwin's publication of The Origin of Species. So over those 150 years, we have learned an incredible amount. We learned that life emerged over 3 billion years ago and was shaped by natural selection and random mutations. We have located and deciphered the genetic code, outlined the basic mechanism of living cells, and discovered the cause of disease. And finally, located the source of consciousness and emotion in the brain, and have started to explore its mysteries. All of this just in 150 years, 2 lifetimes. And 150 years, indeed, is since the publication of the fundamental theory of life, namely natural selection,